So welcome to today's colloquium. So we're happy to have Liam Fitzpatrick. Liam received his PhD from Harvard, working with Lisa Randall, where he started out working on RS models. And I think while he was still a graduate student, wrote famous paper on effective field theories of inflation. And then after his PhD, he went to Boston University and Stanford, migrated into working on dark matter for a while, wrote another very well-known paper on effective field theory of dark matter direct detection in nuclear recoils. And then eventually started working on CFTs, where I think he's found his spiritual home. And so he'll be telling us today what dynamics we can extract from CFT relevant for QFTs. So thanks, Sam.
All right, well, thanks very much for the introduction. Thanks to the organizers for inviting me to give this talk. And also thanks to my wife and parents who are watching my kids and allowing me to be here today. So yeah, today I'm going to talk to you about sort of the connection between conformal field theory on the one hand and quantum field theories more generally on the other hand. And specifically, I'm going to talk to you about how we can use our knowledge of conformal field theory to actually do numeric non-perturbative computations in quantum field theory. So that's kind of going to be the big picture, how CFT informs our knowledge of quantum field theory. But let me back up a bit. So we all care about quantum field theory in this room. We have a dark matter workshop and a bootstrap workshop. So we're all interested in quantum field theory at one level or another. But why is that? The answer is quite simple, because quantum field theory describes pretty much absolutely everything we've ever seen. I don't think that's an exaggeration. It really is quite remarkable. Every area of physics if you look at the smallest length scales we're able to probe experimentally, what you find is described by quantum field theory. All right, this is true, of course, of the Standard Model, most famously, but it's also true of quantum gravity at energies that are accessible to us experimentally. The effective theory of quantum gravity works very well at low energies. And it's also true of beyond the Standard Model physics, things like dark matter and inflation. It's quite straightforward to write down models of these things in quantum field theory that match all available data. In some ways, the problem is it's too easy. We have too many models that work, and we need to experiment to distinguish between them. So this is an impressive success of quantum field theory. And even beyond fundamental physics, there are many areas of what we might call emergent phenomena where quantum field theory describes the system. So probably the most famous and well-known is the theory of critical phase transitions. So really quantum field theory is everywhere. As far as what we can see, it's sort of the language that nature speaks. And we're interested in the full range of what can happen in quantum field theory because we want to learn to speak this language as fluently as possible. All right. So just studying quantum field theory for its own sake at this point, I think is an important goal. And as soon as you start to try and explore what's possible in the full range of QFT, you immediately run into a problem, which is it's very hard to do much at strong coupling. Okay. This is in contrast with weak coupling, where perturbation theory is a pretty generic tool. It's a very powerful, sharp tool, which allows us to very quickly see what should happen, whereas at strong coupling, we're much more limited. And this is sort of true in any application of QFT. I think it becomes emotionally very tangible, for instance, in beyond the standard model building, where at weak coupling, perturbation theory is, we kind of have turned into a little factory that we can use to sort of mass produce models. Whereas the situation at strong coupling is really kind of the opposite. It's kind of a Wild West. And for most strongly coupled theories, the most we can do is we can make some conjectures. We can maybe try and parameterize the result, but we're much more limited than we are weak coupling. All right. So we would like to understand QFT as strong coupling. We'd like a practical method that allows us to do computations as strong coupling, all right, for sort of generic theories. This is an important problem. Lots of people have spent a lot of time working on it, and there are several different approaches for it. Probably, I've written a couple of them up here. Probably the most well-developed is lattice field theory. There's a thriving community of physicists who have dedicated their whole careers to developing this tool, and it's very powerful. There are a couple others that I've written up here. So there's what you might call sort of improved perturbation theory. That is taking what we know in perturbation theory and trying to resum it in one way or another. And then I've written on two more approaches up here, conformal bootstrap and Hamiltonian truncation. And today I really want to talk about number 4, Hamiltonian truncation, but also to some extent its relation to number 3, the conformal bootstrap. All right, so this is what I'm going to be discussing today. But before I get into that, I want to mention just a few words about why you might like to have a complementary approach to the lattice. So lattice field theory is a very powerful method, but it does face some challenges. It's not always possible to put a theory on the lattice. Probably the most important example of this is chiral gauge theories. Chiral gauge theories are very interesting. They're also the world we live in. The standard model is a chiral gauge theory. Another reason is that the lattice, space-time in the real world is not a lattice, and that the lattice can actually have physical effects, which you don't want. So in particular, one example is if you're looking at, say, hydrodynamics, where the temperature is greater than the lattice spacing. So the fact that the lattice breaks translation invariance means you can actually lose momentum to the lattice, which is not what happens in real fluids. So this process of losing momentum to the lattice, these are called Umklapp processes, and they lead to very different physics from what you would see in a real fluid. And then finally, one final challenge of the lattice is it's usually done with Euclidean Monte Carlo. So the quantities that are easiest for it to extract are Euclidean quantities, but we're of course very interested in real-time Lorentzian observables, right? And it can often be very difficult to extract those from Monte Carlo. All right, so these are some reasons why, despite the success of lattice field theory, you might like to have some other methods in hand. And so that brings us to conformal field theory and what it can help us say about strongly coupled quantum field theory. All right, so let me back up a little bit, and I just want to talk a little bit about sort of the role that conformal field theory plays sort of in the sort of ethos or psyche of the physics community. And I think this was the attitude that physicists had for a long time. It certainly was the attitude I was taught as a grad student, that conformal field theories are kind of these precious little objects. They're very hard to find. You have to do weird things, like you have to tune a lot of parameters. You might need an enormous amount of supersymmetry to make beta functions vanish. They might be very beautiful objects in their own right, but you kind of have to search far and wide to stumble across them. And one place that this perspective is sort of very clearly stated is in Coleman's Eriche lectures. He actually has an entire Eriche lecture about conformal field theory, about scale invariance. And it's a very strange lecture. So he starts off in the first half of the lecture by talking about the implications of conformal invariance. And he's going along and he's getting these interesting results. And then about halfway through, he says, okay, but there's a problem. This is actually all BS. In his colorful way, he says the entire theoretical structure of conformal field theory is a lie. Right, this is the direct quote. You can look it up. That's what he says. And basically what he means is that they're beta functions, right? Once you start doing loops, you find that couplings run. And so theories, even if you make them conformal at the classical level, they won't be conformal at the quantum level. So he says, okay, so conformal field theory is kind of a hoax, and then he goes off, and for the rest of the lecture, he goes off in a different direction. And then at the very end, he kind of circles back around, and he says, all right, well, maybe we were a little too harsh to conformal field theory. Maybe there is something there. And he says, how could a theory end up actually being scale invariant? He says, well, one possibility is that the beta function might have a 0, okay? It's not good enough for it to have a 0. The actual value of the coupling in our actual world for some reason, has to sit at the 0. But if that were true, then the theory really would be scale invariant. And then he says, I have really no idea why the coupling would ever sit at the 0. But my good friend Ken Wilson says there's some very good reason why the coupling actually should sit at the 0. And I have no clue what he's talking about. Okay. So of course, we all know what Ken Wilson was talking about. He was talking about fixed points and universality. The idea that no matter what the coupling is in the ultraviolet, it's going to flow toward the fixed point as you go to the infrared, and the theory will become conformal in the IR. And I love this quote. I love quotes like this because I think they help to demonstrate how we evolve as a community. How some notions start off being kind of foreign, and then little by little they kind of become part of our language and part of our way of thinking. So all of you, I don't even really have to explain what this picture is. Instantly know what Ken Wilson was talking about. But it was sufficiently alien in the 70s that Sidney Coleman decided to make a joke about how confusing it was. Okay, so now conformal field theory is starting to re-enter the picture. What Ken Wilson taught us is that the way to think about quantum field theory is to organize it by energy scale. This is how you should think about quantum field theory. And sort of the cartoon of you look at a picture and you coarse grain it and you ask what happens as you coarse grain it. And in particular, you should ask what happens to the theory as you change the energy scale that you're looking at. And all interactions you should ask, are they relevant? That is, do they become more important at low energies? Or are they irrelevant? That is, do they become less important at low energies? And quantum field theories are just RG flows. They're just points on RG flows between conformal field theories. So now we start to see CFT re-enter the picture. Okay, so quantum field theories are points along RG flows, and the endpoints of those RG flows are CFTs. All right, and so to think about quantum field theory, you can start with the CFTs, and if you take a conformal field theory, and you add an irrelevant deformation to it, not really very much happens as you go to the IR. You just flow back to where you started. But if you add a relevant interaction, now that becomes stronger in the IR, and it pushes you down some RG trajectory towards another fixed point. And QFTs are points along this flow. So here we have a picture where rather than CFTs being sort of isolated little curiosities, they're actually central to our understanding of what quantum field theory is. Right? The idea is first you should understand the conformal field theories, and then you understand quantum field theory as points along the RG flow between them. All right. So I like this picture very much. I find it very compelling and beautiful, but it's kind of a cartoon at this point. And so it'd be much nicer if instead of just being sort of some philosophy, if we could actually make it really concrete and practical. That is, can we actually use this picture as a practical computational tool for computing things in quantum field theory? All right, so that's the goal. And I'm going to show you how we can do that, right? So here's the basic idea, how we are going to numerically solve RG flows. So we're thinking about, in the picture I just described, we're thinking about theories as being a CFT plus a relevant deformation. In this talk, I'm going to stick to the Hamiltonian language. So we have a Hamiltonian, which is one contribution from the Hamiltonian of the CFT, and then it has another term, which is a relevant operator in that CFT. Okay. And how do we solve this theory? We just solve the Hamiltonian. All right. It doesn't sound so hard. How hard can that be? All right. So here's the modest proposal for solving all of quantum field theory with two weird tricks. If I said one weird trick, you would know it was clickbait, but no, it's two weird tricks. So step one, you solve the CFT. And this is sort of what the bootstrap is about. And step two, you solve the RG flow. All right, so you might be skeptical that this is ever possible. You might be a little more willing to suspend disbelief for step one because conformal symmetry is present in step one, and the constraints of conformal symmetry are actually surprisingly powerful. All right, the fact that they're so powerful and rigid is what's behind the conformal bootstrap, and it's what a large part of what lets strongly coupled CFTs be solved by the bootstrap. Where you might be more skeptical about step two, now there's no conformal symmetry. You don't really have any special symmetry anywhere. So you're probably much more pessimistic about this. But what I'm going to tell you is, in some sense, step two is actually the easier step. All right, that is, if someone comes along and performs step one for you, and they just hand you the complete solution to the CFT, all of what we would call the CFT data, and they just give it to you. Step 2 is actually not that hard. All right. And I'm going to explain why that is. And the way you use the CFT data to perform step 2 is a method called Hamiltonian Truncation. Hamiltonian Truncation is an example of a variational method in quantum field theory. As far as I know, it's basically the most successful method, successful variational method in quantum field theory. And so let me tell you a little bit about what that is. And I'm going to do this with a simple warm up. Probably the simplest example I know is the anharmonic oscillator. And so this has some structure, which we'll be coming back to in QFT. The important structure here is that there's a part of it, which is a solvable Hamiltonian, the simple harmonic oscillator part. And then there's another part, which is the interaction term x to the 4. All right. And the basic idea of how Hamiltonian truncation works is we're just going to diagonalize this Hamiltonian numerically. All right. So to do that, we want to turn it into a matrix with concrete entries. And so we have to choose a basis. So sort of a natural basis to choose is the basis that diagonalizes the part we know how to solve. All right, the simple harmonic oscillator part. So let's choose a basis for this Hamiltonian of harmonic oscillator eigenstates. All right, those are, as we all know, those are just states created by raising operators. And one nice thing about this basis, so first of all, by construction, it diagonalizes the harmonic oscillator part. And the interaction part is actually, it's very easy to compute the matrix elements for that guy, right? Because X is just A plus A dagger. And so you can very quickly compute this matrix elements. So in this basis, the Hamiltonian is just a giant matrix, right? It's just a giant list of a whole bunch of numbers. And the way we solve the theory is we just throw that giant matrix on our computer and we type in eigensystem and we hit shift enter. Okay, there's one little problem, which is that it's an infinite dimensional matrix. Unfortunately, despite advances in hardware, computers still are not able to store infinite by infinite matrices, maybe in the future, but not yet. So we have to do something to make it a finite matrix. And the simplest way to do that, just take a finite submatrix. All right. So choose some maximum harmonic oscillator number and max, and keep all of the states up to that point. And then throw that thing at your computer and diagonalize it, and make n max as big as you can. And the bigger it is, the more accurate your answer will be. And this is sort of an unusual case in that the convergence is extremely fast. But in any case, the idea is sort of general that as you take the size of your basis larger and larger, your answer becomes more and more accurate. All right, and you get all of the eigenvalues of the spectrum. Okay. So I really want to emphasize how simple this is. This is a particularly simple example, but is remarkably simple and easy to implement. So just to emphasize this, I've actually written out all the code you need to do this calculation. You can literally write this in less than 5 minutes. I encourage you all in your spare time to try that. It is extremely satisfying. If you take these lines, and type them into Mathematica, you will actually get a plot of the eigenvalues of this anharmonic oscillator. All right, I really don't think there's any other method that is as fast as this. It's just extremely easy and fast. All right, and it works at strong coupling. Okay. Yeah. Too late, you missed your chance. Now you have to try and write it yourself. All right, good. Okay, so hopefully the idea of what Hamiltonian truncation is relatively clear. It's a pretty simple idea. And we're going to apply the same idea to quantum field theory. All right. So now we're going to have similar structure to what we had with the anharmonic oscillator. We have one piece, the CFT piece, which we're going to assume has been solved for us. And we're going to have another piece, which we add to it, which is the interaction, which, as we were describing, we're going to add relevant interactions. These are going to be relevant operators in the CFT. Okay. So let me give you a real simple example. The simplest example I know of a CFT is a free massless scalar. It's a perfectly respectable CFT. And And this has relevant deformations. So for example, you can add a mass term, phi squared. And as long as you're in fewer than 4 space-time dimensions, you can add phi to the 4. That's also relevant in d less than 4. Okay. And then now we have to choose a basis to evaluate the matrix elements in. And the basis we're going to choose, we're going to try and as much as possible take advantage of the conformal structure of the UV fixed point. Okay. So we're going to choose a basis of states created by CFT operators. So in a minute, I'll say in great detail exactly what that means. But we're going to take states which are somehow created by CFT operators. And we're only going to keep the ones which are created by operators with dimension below some cutoff. Okay, and then we're going to try and take that dimension as big as we can. In all cases, we'll have a finite matrix. We just throw it at our computer and diagnose it. All right, so that's the idea. Okay, so I lied. I'm not going to tell you the details of how we create states for CFT operators. I'm just going to try and focus on the big picture here. If you're interested, I'm happy to talk about it afterwards. There are actually a couple different ways of doing it. But the important point is our states are associated with operators in a specific way. And the reason this association is useful is now the matrix elements of the Hamiltonian are completely determined by what we think of as the CFT data. All right, so when we talk about the CFT data, what we're talking about is the 2-point functions and 3-point functions of the CFT. That's what we normally refer to as the CFT data. And you can see that that's enough to information to get the matrix elements of the Hamiltonian. So the CFT part is basically like a 2-point function, the CFT Hamiltonian matrix elements. And the deformation, since the deformation is itself an operator in the UV CFT, its matrix elements are like 3-point functions. Okay, and the reason we call 2- and 3-point functions the CFT data is these are completely fixed by a discrete set of numbers, the scaling dimensions and the OP coefficients in a CFT. All right, so there's the discrete set of numbers. And if you know the two scaling dimensions and the OP coefficients in the CFT, then by using the operator product expansion, you can compute any correlation function of any number of operators, any endpoint function in the theory. All right, so it's sort of a complete set of information. And it's sort of naturally related to what we're trying to do in Hamiltonian truncation here. Okay, so that's the idea. All right. This is why if someone solves the CFT for you and they hand you the solution, you already have the Hamiltonian, and then you just diagonalize it. Okay. All right. So now that we've gone through all this introduction, let's look a little bit at an example. So here's probably the simplest example we could look at, which is phi-4 theory in 2 dimensions. And let me just remind you what we expect in this theory. So at weak coupling, it's easy to understand what should happen. The theory has a mass that is very close to the bare mass of the theory. The field sits at the origin, so there's a Z2 symmetry in this theory. And at weak coupling, phi sits at the origin, and that symmetry is respected. Once you start cranking up the coupling, first the mass starts to come down, and eventually the mass squared gets renormalized to be negative. And if the coupling is large enough, you actually destabilize the scalar, and it rolls off to a new minimum away from the origin. At that new minimum, the Z2 symmetry is spontaneously broken, and you have a new mass for the fluctuations around the new minimum. Okay. And then probably the most interesting point on this whole diagram is the point between them, the critical point, where the gap closes and the theory becomes a CFT. And in this particular example, the critical point is described by the 2D Ising model. That's not obvious, but it turns out to be true. Okay, so this is what we expect in this theory. So let me just show you an example of what you get from truncation. So here, what I've done is I've taken a very low truncation, which only has 3 states, delta max of 3, and I've plotted the gap as a function of coupling. And you see it starts off at weak coupling very close to the bare mass. And as you crank up the coupling, it drops down and crosses zero. With such a low truncation, this is not a particularly accurate answer, but the point is that you can keep increasing the truncation and the answer becomes more and more accurate. By the time you get to delta max 30, it's actually converged pretty well, and at delta max 40, it's converged extremely well. All right, so this gives you a very accurate calculation of what the gap is non-perturbatively as a function of the coupling, and you see where the fixed point is. All right. Okay. So that's one example. We'll come back to this theory a little bit later. But next, I wanted to move to a slightly more complicated example, which is a little richer, the theory of QCD in 2 dimensions, specifically in the limit where the quark mass is very small. So this is a very interesting theory. So I'm going to talk a little bit about how we understand what happens in the infrared in the limit where the quark mass is small. So when the mass goes to 0, the theory actually has a sort of a Goldstone boson pi. I put Goldstone in quotes because there are no Goldstone bosons in 2 dimensions. But when the mass is 0, there's a massless pion in the IR. And the way to understand that is the UV theory has an anomalous axial symmetry, and that anomaly has to be reproduced in the IR by a massless state. But it's actually easy to say quite a bit more than just that there's a massless pion. You can actually say precisely what its decay constant is. So I'm going to go through this because I think it's kind of cool, and we'll use it in a little bit. So the way this works is pretty simple. So in the UV, we have an axial current, which I've written in terms of the quarks. Okay, and you can compute the anomaly coefficient very easily. It's in 2 dimensions. It's just a 2-point function of currents. So it's just a 1-loop diagram. And the coefficient is the number of colors divided by 4 pi. In the IR, we have the massless pion. And under the axial symmetry, that has to shift by the decay constant. So we know that the axial current has to be f pi times d mu pi. So the transformation of pi is the correct one. And in the IR, it's also very easy to compute the 2-point function of the current and read off the coefficient of the anomaly, and it's just f pi squared. And by matching the UV and the IR, you see that the decay constant satisfies this relation I've written here. F pi squared is the number of colors over 4 pi. And this is an exact relation. Okay. All right, so we know exactly what the decay constant of the pion is. We can go farther in the limit where the quark mass is small. We can work out what the potential for the pion should be. So if the quark mass is small, we can do a spirion analysis. And just at small quark mass, we write down the quark mass and we let the mass transform under axial transformations, which have to be compensated for by e to the I pi f. And you immediately see that the potential is a cosine potential. So in the IR, this theory is the sine-Gordon model. This result was actually first derived by Paul Steinhardt in 1980 using different methods. But so we actually know, as a result, we know quite a lot about what the theory in the infrared should be. All right, it's the sine-Gordon model. We know what the decay constant is in terms of the number of colors. And one nice thing about this is the sine-Gordon model in 2 dimensions is exactly solvable. Right, so this allows us to compare predictions of the sine-Gordon model to what we get for truncation. All right, so let me just show you an example of this. One of the things that the sine-Gordon model predicts is that there should be a bound state of 2 pions. It tells you exactly what the binding energy is. It's just this formula. And for the specific case of 3 colors, that's about a binding energy of about 10% of the mass of the pion. And here I've compared that to what we get from truncation. All right, so on the y-axis, I have the mass squared of the different states. And on the x-axis, I have the truncation, delta max. And there are a couple different lines here. So let me just talk about what's going on. The red line is the mass of the pion itself that converges extremely quickly. There's a black dashed line, which is the multi-particle threshold. That's the 2 pion mass. And then slightly below that, I've drawn a brown line, which is the prediction for the energy of the bound state. All right, so it's slightly below twice the mass of the pion. And you can see by delta max of about 6, the truncation result is very close to the prediction from Sine-Gordon. And by delta max of 10 or 12, it's indistinguishable. Okay. All right. So this is an example of stuff you can do with the spectrum. But part of what I want to emphasize about Hamiltonian truncation is you get much more than just the spectrum. Right? You have the full Hamiltonian, you've diagonalized it, so you get not just the eigenvalues, but also the eigenvectors. Okay, and those eigenvectors contain an enormous amount of information. One thing you can do with them is you can just compute spectral densities, right? So when we took QFT, we learned about the Chilean-Lehman spectral decomposition, and we saw a formula like this. And we usually didn't imagine actually, computing it this way, because we didn't imagine we'd have access to all of the states that go into this formula. Usually we use it to prove other things, but here you actually have access to all the different components that you need for this formula. You have what you need is the overlap of the operator with the eigenvectors, but you have the eigenvectors, and you also have a delta function at their eigenvalues, and you know those as well. So you can literally just take what you get from diagonalizing the Hamiltonian and plug them into this formula and add them all up and get the spectral density. Okay. All right, so spectral densities are useful. They encode things like correlation functions using the Chilean-Lehman spectral decomposition. Would see when you probe the system with that probe. So classic example of this is E plus E minus the hadrons. We're sort of probing QCD through the photon, and here the cross section is the spectral density for the current. All right. So here's just another example of the kind of thing you can get from truncation. Here is the spectral density for the current in this theory, and you see it has various interesting features. It has the bound state that we talked about. It has a multi-particle continuum that turns on at twice the pion mass, and then there's actually a resonance, an unstable state, a little bit higher. Okay, so this is. It's not a cartoon. This is a result of a numeric computation. All right. So okay, so you can using the eigenvectors of the Hamiltonian, you can actually compute dynamical quantities of interest. Yes, she.
So in this case, the UV CFT is just the three-gauge theory.
Yes. Yeah, it's just a free fermion.
And the resonance deformation is not gauge invariant, right?
That's right. Yeah.
I guess your density is actually discrete, but you average over it.
Yeah, that's a good point. So I've in order, so the Hamiltonian is a finite matrix, so the spectrum is discrete, as you said. So I've done some smearing to turn it into a continuous spectral density in order to make this plot. That's right. Oh, sure. Yes. Thank you. Yeah. Thank you. Yeah. The question was, isn't the spectrum actually discrete in this case instead of continuous? And because of the finite truncation, that's true. The spectrum is always discrete, whereas in field theory and infinite volume, we really have a multi-particle continuum. And so in order to make a continuous plot here, I did some smearing. Okay. All right. Yeah, so coming back to Xi's question, so the question was, the UV theory is just a free fermion. You've deformed it by turning on the gauge coupling. The deformation is not actually gauge invariant. What was the rest of the question?
Well, does that cause a problem?
The answer is it generally does cause a problem in 3 dimensions or higher. And in fact, this is exactly why. So I'll talk about. So the reason I'm doing gauge theories in 2 dimensions is because we know how to deal with this problem in 2 dimensions. It's basically solved by going to light cone gauge. In 3 dimensions, it is a serious problem and is actually the major obstacle with applying this method above 2 dimensions to gauge theories. Yes. All right. So the preserving gauge invariance in a Hamiltonian truncation method is difficult in 3 dimensions or higher. Good. So let me just talk a little bit about the history of this method. It's actually been around for about 3 decades. It was first introduced by Yurov and Zamolodchikov, where they had the idea of using a basis which was directly connected to the UV CFT operators. It's called the truncated conformal space approach. They applied it to deformations of solvable 2D CFTs. There's another version of this method which involves light cone quantization, which started around the same time. It was developed by people like Pauly, Brodsky, Pinsky, and Wilson. This is actually what Ken Wilson spent a significant fraction of the later part of his career on, and was trying to develop this method. They didn't have a connection to the conformal basis. They were using a basis that was unrelated to conformal symmetry in the UV. And that took until fairly recently in 2013. Ami Katz, Gustavo Torres, who's actually here in the audience, and Yuming Xu formulated the light cone quantization method in terms of states which were directly related to the conformal theory basis in the UV. But sort of the point I want to make is, this has been around for a while. There are probably a few hundred papers have been written using these types of methods. So why aren't they more widely used? And the reason is there are still challenges in applying them. So here I'll mention sort of what are the big challenges. The first challenge is just getting enough states is hard, right? So I said, the idea is you take a big matrix and you diagonalize on your computer. Your laptop can really only diagonalize matrices of about 100,000 by 100,000, maybe a little bit more, but not much more. But there's another problem, which is actually, it's difficult to even compute, to even determine what the matrix elements of the Hamiltonian are. And this is true even in an integrable solvable CFT. And surprisingly, it's true even in a free theory. We think of free theories as being kind of trivial and solvable, but if you want to compute the OP coefficients, all the 3-point functions of all primary operators in a free theory, that's actually quite difficult and computationally intensive. So this is the sense in which, if someone really solves a CFT completely for you, step 1 in this slide from a while ago, and hands up data to you, they've kind of done the hard part. And diagonalizing the Hamiltonian is relatively easy by comparison. The second challenge is that you have non-local counterterms or state-dependent counterterms. So this is easy to understand. This is just related to Hamiltonian formulations. So if you have a truncation on energy, that's a very non-local thing to do. All right, if I demand that the maximum energy of a state is some cutoff value, that knows about the energy throughout all space, right? So if I have some heavy particles off in Alpha Centauri, then my cutoff here on Earth is a little bit lower. So we usually don't do cutoffs on energy. We do something slightly different. And so cutoffs on energy are non-local, and it's harder to deal with, to regulate divergences as a result. And the final reason is related to Xi's question. Preserving gauge invariance in greater than 2 dimensions is a challenge, right? So we know how to do it in 2 dimensions, but above 2 dimensions, it's quite difficult. Yes, Xi.
Just related to that, I mean, the usual CFT axioms do not actually incorporate free gauge theories in dimension not equal to 4. I guess maybe that's not essential for you because you just need to have OP data.
Yeah, I mean, oh yeah, well, so the same ones that, the UVC, I'm not sure I completely understood the question. It was that UV CFTs, the CFT axioms don't usually include sort of free gauge theories as an example. I think you mean in the sense that, they're not sort of connected to interacting CFTs by relevant deformations in the standard way of thinking. Is that what you're talking?
They don't have, like, for example, 3D one gauge theory.
Yeah.
But I guess perhaps that's not important for your application.
Yeah. If I don't think I'm going to have time to talk about it, but the way I would try, maybe I'll say it in words now. So the question is, in free gauge theories, we don't think of those as being CFTs. The fact that you take a quotient does, can by itself break the conformal symmetry by making it hard to fit states into representations of the conformal symmetry. But so let me just say a few words now about how you might try and do something in higher dimensions. I think the approach that you would try and take is instead you would try and start with an interacting gauge theory CFT, which that's something like imagine QED and its conformal 3D QED and its conformal window with some number of flavors, and then that is a perfectly valid CFT. If the number of flavors is very large, then you can do a perturbation theory, and then you can try and deform that thing to reduce the number of flavors. So that's the kind of, I think that's, from a theoretical point of view, that approach is under better control than starting from the free theory and deforming it. Okay. All right, but okay, good. So I said that yeah, there are a number of challenges. Part of what got me interested in this was a couple of papers from a few years ago trying to push these applications to higher dimensions. So in 2013, Matthias Hogverst, Slava Rychkov, and Balt van Ries wrote a paper showing that you could do TCSA in greater than 2 dimensions. And then there was a paper shortly after using the light cone formulation by Ami Katz, Zuhair Kankar, and Matt Walters, showing how to extend that to greater than 2 dimensions. And then there's been progress since then. And just a year ago, there were 2 papers, one in each method, doing phi-4 theory in 3 dimensions and getting fairly precise results. So the main obstacle was figuring out how to do a regularization and handling the state-dependent counter terms. And so they have a much better understanding of how that works. So let me just show you a couple of results that they got. The first one I wanted to show you is the spectrum of the theory as a function of coupling. So here what I'm showing you is the gap for the 1 particle, 2 particle, and 3 particle states. And so the green, blue, and red respectively as a function of coupling. And as you crank up the coupling, eventually the gap closes, and that's where you hit a critical point. And the fact that all 3 lines hit 0 at the same point is non-trivial. That's not automatic. So that's a non-trivial check. But a much more interesting check is to look at the correlation functions in the theory near the critical point, and these should become scale invariant. And what you see is there's about a decade in position over which the operators' 2-point functions scale in the right way. And so there are 3 lines here, red, green, and blue, for 3 different operators, phi squared, phi 4, and phi to the 6. What's important is that these 3 operators are even under the Z2 symmetry. And so near the critical point, you can expand them in terms of operators of the IR CFT. And so they should all scale the same way. Right? In the weakly coupled theory, that's not true at all. They behave very differently at weak coupling, but near the critical point, they all scale the same way. And you can read off how they scale. From that, you can read off the scaling dimensions. And they match reasonably well with what the known scaling dimensions are in the 3D easy model. Okay. All right. So I think this was a significant progress in applying this method in higher dimensions. So for the last part of my talk, I'm going to go back to this simple theory, a 2D phi-4 theory, and I'm going to talk about one application to basically thermodynamics and thermalization. So this is kind of a natural thing to do. Once you have the entire spectrum of the theory, you might try and study the statistical mechanics of the theory and the time evolution, in particular the approach to thermalization. All right, so I'm going to show you how you can do that in 2D phi-4. So the first thing we'll do is look at sort of the structure of the excited states using form factors. Then we're going to do thermodynamics using the eigenvalue spectrum, sort of, in the way that we were taught to do thermodynamics in college. Then we'll look at also from the eigenvalue spectrum, we can see some signatures of the chaotic behavior of the theory. And then finally, I'll look a little bit at thermalization from time evolution of the system. Okay, so this is where we're going. Okay, good. So let me talk about how you probe the internal structure of states. One way to do this is using form factors. These are matrix elements of local operators. And if you have an in-state and out-state with different momenta, so then you have some momentum transfer through the probe operator. And by varying that momentum, you can sort of map out the internal structure of the particle. All right, so this is a standard way of doing things like probing the charge distribution of something like the proton. There, the operator would be the E&M current. If the operator is the stress tensor, then you probe the energy distribution of the particle. All right, but this isn't limited to just particles. You can do it for any state. So we can use this to learn something about the energetic states of the theory. So here I'm going to use mu to indicate energy. So here, let's just take an excited state and we'll look at its form factor for the stress tensor. And from that, we can kind of read off the size of the object, right? By looking at the leading term in a small momentum transfer expansion that tells us the size of the object. And what this plot shows you, so the x-axis is the truncation, the y-axis is the ratio of r squared over this quantity that I've written here, delta max over mu squared. And what you see is that it's basically independent of delta max and independent of the energy. So it's roughly a constant. So the prefactor in front of delta max over mu squared is basically 0.6, independent of the energy or the truncation. Okay, so what that tells us is that these excited states have a size which is set by a combination of their energy and the truncation. So this is sort of like a finite volume effect. You can think of like we took a ball of gas and we put it inside a box, and the box is this size. Okay, and that's important because we want to know the volume of the states, because we're usually more interested in the energy density than we are interested in the total energy of the state if we want to do thermodynamics. Okay, all right. So that'll be a useful thing to know. So next, let's look at entropy. And here we can just do it the old school way that we learned how to do it, just do entropy by counting states, right? So look some energy window, count all the states that you find and take their log, and that's the entropy, okay? And from that, you can easily compute what the density of states is as a function of energy. And then by dividing by some volume factors, you can convert that into the entropy density as a function of energy density. And you find that over a few decades, it's roughly entropy density goes like square root of energy density. All right, and then you'll notice there are two other features. So at very large energy, the entropy starts to fall off. That's just a truncation effect. That's because we eventually run out of states. There are no more states in the truncation. And then at smaller energies, the entropy starts to shut down. That's a physical effect. Part of that is because there's a gap in the theory and there are just no states below the gap. Okay. All right, so we can read off the density of states and the equation of state just by looking at eigenvalues and their distributions. Another thing we can look at is signals of chaotic behavior by looking at eigenvalue spacings. So this is one of the standard things to look at for signatures of chaos, is you take all of your eigenvalues, you line them up in a row, and you look at the distance between neighbors, and you look at the distribution of those spacings. And in a chaotic system, these are expected to follow what's called the Wigner-Surmise or the Wigner-Dyson distribution. The story goes that there was a conference a long time ago on nuclear physics, and someone randomly asked, if anyone had an idea for what the distribution of energies in atomic nuclei should be. And Eugene Wigner stands up and walks over to the board and just writes down this formula, which is called the Wigner surmise because he surmised it, I guess, or something. But it's actually, the derivation of it is pretty simple. So I just want to say a little bit about how it's derived. Okay, I think it's a nice thing to understand, and it's satisfying to see how it works. The idea is you don't know, the energies of atomic nuclei are very hard to compute. And so, Wigner's bold idea was, well, let's just pretend they're random, okay? And that actually turns out to do pretty well. So imagine that your Hamiltonian is just a matrix with random entries. So here I've assumed it's a symmetric real matrix. So there are 3 independent parameters. You can easily calculate the eigenvalues of this 2x2 matrix, and what you care about is the spacing, which in this case is just the difference between them. And then if you assume that all 3 of these parameters, epsilon 1, epsilon 2, and v, are drawn from Gaussian random Gaussian distributions, then you can do a little bit of work and read off what the distribution of the eigenvalue spacings are. Okay, and this is where the Wigner-Dyson distribution comes from. And the most salient feature here is that notice that there's a factor of the spacing s in front. So when the spacing is very small, the probability goes to 0. And this is due to eigenvalue repulsion. The off-diagonal elements v make it very unlikely that epsilon 1, that the 2 eigenvalues will fall on top of each other. Okay. Good. By contrast, in an integrable system, there's no eigenvalue spacing. So in an integrable system, the idea is that there are a very large number of conserved charges. So any 2 neighboring eigenvalues are expected to come from different charge sectors. So there will be no off-diagonal matrix elements. And so there's no eigenvalue repulsion. All right. So if we look at phi-4 theory on strong coupling, this is what we see. So the blue circles are the eigenvalue spacings. And then the solid curve is Wigner-Dyson, and the dashed curve is Poisson. So it's clearly following the Wigner-Dyson distribution. The fact that it's chaotic at strong coupling is perhaps not surprising. What I think is more interesting is it's actually chaotic even at weak coupling. All right, so to show this, I'm going to look at this quantity eta, which is kind of a measure of whether it's closer to Poisson or Wigner-Dyson. So it's basically eta is in the numerator, it's the difference from a Poisson distribution, and in the denominator, it's the distance from a Wigner-Dyson distribution. So if eta is very small, it's very Poisson-y. If eta is very large, it's very Wigner-Dyson-y. So red is, you should think of as chaotic, and blue you should think of as integrable. And what you notice is as you crank up delta max, the red is coming down. So more and more, so the chaotic region is extending to smaller and smaller coupling. And if you could go to infinite delta max, then you would see chaotic behavior all the way down to arbitrarily small non-zero couplings. All right. And I think this is a nice reminder that although we think of weak coupling as being perturbative, that's really only true when we're talking about small particle numbers. All right. But if we talk about these high energy states where the number of particles is very large, perturbation theory actually breaks down. Right? Perturbation theory is only valid for it breaks down when the particle number of the state is greater than 1 over the coupling. All right, so let me just do one last thing. This will be the last plot that I show. And it kind of combines a bunch of the things that we've looked at so far in one single plot. So I said we would like to look at thermalization. One interesting thing to look at would be to take some state, look at an operator in that state, and see how it evolves over time. And at late times, you expect it should approach a thermal distribution. And it's also interesting to see how it approaches that, which should be described by diffusion and hydrodynamics. And so because you have all the eigenvalues and eigenvectors, you can simply decompose the state into eigenstates, and the time evolution of each of those is relatively simple. For the sake of simplicity, I'm going to look at a simpler quantity. I'm just going to pretend these factors, everything except the exponential, I'm going to pretend it's 1. Okay, that may seem like an ad hoc thing to do, but when you do this, you actually get something that has been widely studied called the spectral form factor. It's nice because it only depends on the spectrum, and it tells you about various aspects of the theory. So that's what I plotted here, the integral of the spectral form factor over time. It kind of has a couple different regimes. At early times, the time is too small to sort of resolve the individual eigenvalues. So you're really only sensitive to the density of states. At late times, you start to see the spacing between the eigenvalues, and then you do start to be sensitive to eigenvalue repulsion and the discreteness of the spectrum. And so what I've plotted on top of, so the wiggly curves are the data, and then I've plotted at early times, the dashed lines are the prediction from the density of states. And at late times, I've plotted the prediction from random matrix theory, which is that due to eigenvalue repulsion, there's sort of this linear growth. And then due to the discreteness of the spectrum, there's sort of a flat plateau at the end. All right, so this one plot kind of has both the density of states that we looked at earlier and also the eigenvalue repulsion and random matrix theory combined on one curve. Yes, she. So the question is this in fixed volume or is it infinite volume? This is, the truncation that this is made in is kind of a hybrid of infinite volume and fixed volume. So it's kind of like that. So what I was trying to convey by this picture of, this star with some size whose size was set by delta max over its energy, you should think of each individual state as living in kind of some fixed volume. So it's kind of like fixed volume. Okay. So good. So that's all I wanted to really show today. Let me say a few words about what I think is interesting in the future. So I mentioned that there's been progress on applying these methods in 3D. It seems like scalar theories in 3 dimensions are now under control. I think fermions are also under control. So it'd be interesting to do a theory with both. It might be possible to implement supersymmetry. There's a lot more to do with transport and hydrodynamics and thermodynamics using excited states, much more than I showed here. You could try and do a model like the O2 model where you can create charge states to try and study diffusion. And then finally, the last point I want to make is that the 2D models the 2D methods, I think, are really under control for a pretty wide range of theories. Pretty much any theory which is sort of a theory of scalars, fermions, or gauge fields with relevant interactions, I think we know how to deal with. And to make it easier to get into, we put out a code you can download and start running it, so you don't have to learn everything from scratch. And there are a lot more interesting 2D theories to be studied. So I think there's quite a lot to do there. So that's it. That's the end of my talk. Thank you all for listening. I hope you enjoyed it.
Thanks for the very nice talk. Questions?
Yeah, so this approach seems to sort of complement the idea of conformal perturbation theory, where you start in a conformal field theory,
Yes.
use for curves of expansion going out. And I guess, as I understand, if you want to go to a general quantum field theory that's a little too far away from a CFT, conformal perturbation theory won't work very well. Do you think this is going to work well in the case for a conformal perturbation theory?
Good. So the question was, this is sort of complementary to what's called conformal perturbation theory. Conformal perturbation theory is the same sort of setup. You're thinking about a CFT with a relevant deformation, and you do perturbations in that deformation, and that works well in the ultraviolet, and then always breaks down in the IR once that perturbation starts to become strong, or it usually does. There are some exceptions. And so the question was, is this sort of complementary to that, in that it could let you actually go past the point where conformal perturbation theory breaks down? And indeed, that is exactly the point, that this is a non-perturbative method which lets you go all the way into the infrared and explore what happens even once the deformation becomes strongly coupled.
Do you have examples where you can then use that to see how to expand conformal perturbation theory by some re-information?
Well, that's a very interesting. So the question is, does this give you some guidance on how to resum conformal perturbation theory? That's an interesting question. I don't have any ideas for how you would do it, but maybe there is something. Okay.
I would guess conformal perturbation theory generically converges if the CFTs interact. It's only with a special example free theories, that's.
So the statement is conformal perturbation theory generically converges. No, that's not true. It normally does not converge.
Wait, how do you know that? I mean, there are plenty of examples.
There is examples of short RG flows. There are some examples, but I think these are the exception. Usually conformal perturbation theory does not converge.
I'm not sure about that. I mean, you can, there are many, like take A plus 4 supreme node, generic quantum moduli space. We believe that the conformal theory should have finite rates of convergence. It's only at the cusp where the rates of convergence, where you don't expect to converge, right? And you take to the zero component on the Fabio manifold, the generic quantum moduli space, we also think the
Yeah. Well, why don't we talk about it? I think usually conformal perturbation theory is an asymptotic expansion. Of course, there are exceptions, but I think generically it's an asymptotic expansion. But okay, you disagree. But yeah, why don't we talk about it? Yes. Sorry, can you say that a little louder? Okay, yeah. So the statement was yes. The question was the entropy is going like square root of energy. Is that something that follows from bioscaling? And the answer is yes. Another way of saying is this what Cardy predicts? What? 1 plus 1D. This is 1 plus 1D. So this is another way of saying this is the prediction for the Cardy, which is the prediction of the fact that in the UV, so it's a relevant interaction, so at very high temperatures, it's weakly coupled and it should be described by Cardy growth. Can you say it again? Would be a different power, likely. Yeah. Yeah. Yeah, probably. I think it'd just be a different power. Yes, Tom.
Do you have an estimate for how many states you would need to study transport in 2+1 dimensions? And is that
Yes, the question is, how do I have an idea of how many states it would take to study transport in 2+1 dimensions? The honest answer is no, I don't. But yeah, I don't have an estimate of how much it would take. It's a great question. It's not been done at all, and I think more or less the tools are available to try doing it. I don't know how many states you would need to get good results.
All right, so thanks, Sam, for the very nice talk. Thanks, Sam. We can continue our discussion outside.